Hello everyone. In the previous session I have done a concept of Cauchy's residue theorem. So anyhow we need to solve problems based on Cauchy's residue theorem. Let me do it after completion of the theorems. So here is the theorem. So argument principle theorem. Statement is, let gamma be, this is important theorem, if gamma is a closed curve and f of z is meromorphic function, as I already explained the concept of meromorphic function, inside and on a closed curve gamma and f of z does not contain any pole gamma, let n be the number of zeros and gamma be number of zeros inside gamma, and let p be the number of poles of f of z inside gamma, then we have to prove that this statement is true, where n is the number of zeros and where p is the number of poles. So clearly in the statement it is given. Now coming to the proof, you have to memorize the statement along with the proof. Fine. So coming to the proof, let us consider a function, since f of z is analytical, right? So let us consider a function f dash by f of z which is analytical. Meromorphic meaning is it is analytical everywhere except at the poles, right? So if f of z is meromorphic in the sense which is analytical except at the poles, then I can write f dash of z by f of z is also analytic except at zeros and poles of a function f of z. This is the meaning of a meromorphic function. So if f of z is meromorphic, I can say f dash of z by f of z is also meromorphic in the sense f dash of z by f of z is analytic at all the point except at poles and zeros. Fine. Let f of z has, next let us consider a function f of z which has a 0 of order k at z is equal to a, or else I can say let z is equal to a be the 0 of order k of a function f of z. Fine. Now what I'm going to do is I'm going to differentiate, or else since z is equal to a is a 0 of a function, I have chosen this as a 0 of a given function f of z. So as per the definition of multiplicity of 0 or 0 of multiplicity, we have f of z can be written as z minus a power of k into g of z. This is the definition of 0 of multiplicity k, where g of z is clearly not equal to 0, right? I'll just repeat once again. Since f of z is meromorphic, as per the definition of meromorphic, the function will be analytical at all the point except at zeros and poles. So if f of z is meromorphic, I can say f dash of z by f of z also satisfies the same condition. And I have chosen z is equal to a as a 0 of order k. So as per the definition of 0 of multiplicity k, I can write this statement, where g of z will not be equal to 0. Now what I am going to do is I'll just differentiate this equation with reference to, or with respect to z. So when you're going to differentiate with respect to z, you will get f dash of z as z minus a power of k minus 1, that is k into z minus a power of k minus 1. Differentiation of x power of n is n into x power of n minus 1, something like that. Clear? Into g of z. Plus, since it is a function of z, we have to apply product rule. First function g of z into derivative second function is this, plus second function is g minus a power of k into derivative is g dash of z. Clear? Now I can rewrite this as f dash of z. Let me take common term, that is z minus a power of k minus 1. I will take common. So you will get k into g of z plus, since z minus a power of k minus 1 is a common term, since we have only k here, so we can write z minus a into g dash of z, right? Why? Because when you're going to take common factor, you will get z minus a power of k minus 1 here. Power k get cancelled, you will have minus 1 here. So when you shift it to numerator, you will get z minus a here. Hope so this step is clear. Now here f dash of z I have solved. And moreover it has a 0 of order k minus 1. Why? Because it is having the power k minus 1. I'll just write the statement, f dash of z has 0 of order k minus 1. Now let us consider f dash of z by f of z. Fine. Just I'll divide this f dash of z with the function f of z. F of z I have taken here and f dash of z is here, so I am going to divide. You will get z minus a power of k minus 1 into k of g of z plus z minus a into g dash of z divided by f of z is z minus a power of k into g of z. Fine. So z minus a power of k into z. I'll just write one more step in order to understand well. F of z, since I am going to split this term, so I can write z minus a power of k into z minus a power of minus 1. We can write like that, right? So k into g of z plus z minus a into g dash of z divided by z minus a power of k into g of z. Now z minus a power of k get cancelled. So what you left with is f dash of z divided by f of z will be equal to z minus a power of minus 1 into k into g of z plus z minus a into g dash of z divided by g of z. Fine. Now I am going to split this term so that you will get. I'll just continue here. See, we can write f dash of z divided by f of z as, see, k into g of z divided by g of z into z minus a power of minus 1. Just multiply this. Since all these steps will not be there in the notes, please go through the video. So I am going to multiply, at a time I am going to divide. Plus z minus a power of minus 1 into z minus a power of plus 1. So we will get z minus a power of minus 1 plus 1. Right, into g dash of z divided by g of z. Now g of z get cancelled. You will get k. I'll just shift this term to denominator so that you will get z minus a. Plus, since here minus 1 plus 1, anything power of 0 is 1. So you will get 1 here, g dash of z divided by g of z. So let me take this as equation 2. F dash of z divided by f of z. Clear? Hope so. Whatever I have done, it is clear for you. Next, what I am going to do is equation 2 shows that g of z should not be equal to 0, right? If g of z is not equal to 0, this will never go to infinity. Meaning is g dash of z divided by g of z has no singularities. So it will never become infinity. Meaning is it has no singularity. Therefore, it will become analytical. So I can write g dash of z divided by g of z is analytical inside the curve gamma. Fine. Now f of z is a pole of order minus k at z is equal to a. Right? That is what we have assumed. Fine. Z is equal to a is a 0 of order k of a function f of z, or it is a 0 on, it has both 0 and pole. So I can write f of z has a pole of order k, order minus k at z is equal to a. Right? Why? Because when you replace a with minus k or z with minus k, that will become a pole. I'm sorry, z is equal to a minus a will be 0. Right? So anything anything divided by 0 will be infinity. So that will become a pole. Z is equal to a will be the pole of this function. Right? First term. So I can write f of z is equal to z minus a power of minus k into g of z as per the definition of a what we say zeros, multiplicity m. See here we have considered 0 of multiplicity k. So here it is multiplicity k. So multiplicity same as order. So I have written k here. Here it is an of order minus k. So in place of k I have written minus k here. Fine. Now I am going to differentiate with respect to z. So when you do that, you will get f dash of z is equal to n in the sense minus k into z minus a power of minus k minus of k plus 1. Right, minus as a common term, so into second function plus second function is z minus a power of, see here, first function into derivative of second function plus second function into derivative of first is g dash of z. Now follow the same step, divide it with f of z. Since first step is for order k, next I am doing it for order minus k. So for order minus k I am doing the same procedure. So when you are going to divide, after following all this procedure, you cannot, there is no necessity to write all these steps. You just write directly this step. So when you are going to divide, instead of k, what you are going to get? Minus k. Why? Because it is of order minus k. So when the order is k, here what I have obtained? K. So when the order is minus k, instead of k, I am going to write it as minus k divided by z minus a plus g dash of z divided by g of z. Let me take this as equation 3. Fine. So from equation 3 we can note that for each pole of a function f of z, we get f dash of z by f of z as simple pole with residue minus k. Right. So by Cauchy's residues theorem, what we can write? See here, by Cauchy's residue theorem, what is the Cauchy's residues theorem? Says that mu of f dash of z divided by f of z into dz is equal to, I have done this theorem in previous session. Please go through the videos of Cauchy's residue theorem. So just a statement, summation of all the residues, right? F with reference to ak. Now I can write this as 2 pi I into n of k, that is number of poles at point K plus pole. This is n is none other than zeros, p is none other than poles, p with reference to k. So I can write this as 2 pi I into n of k is simply n minus p of k is poles. So n minus p. Or else I can write this as, I'll just shift 2 pi I to this side, so I'll get my 1 divided by 2 pi I integral over gamma f dash of z by f of z into dz will be equal to n minus p. So this is from Cauchy's residues theorem. So f with reference to ak is none other than number of residues, as this function has both n is number of zeros as well as poles. So residue consists of both poles as well as zeros. So this is number of zeros and this is number of poles. So I can write this as n minus p. So here is the next theorem. It is called as open mapping theorem. It is also important. So statement, either you can write or you can write this, since it is very small theorem, so it is better to write both the statement. So it says that if G is a region in the complex plane and f is a non-constant analytical function in G. Non-constant in the sense it is not a constant, that's all. If U is a open set in G, then f of U is a open set. That is, a non-constant analytical function maps an open set into an open set. Fine. So this is called as open mapping theorem. Let me prove this theorem. Let us consider a open set U in a complex plane. So I am going to consider a open set U in a complex plane G. Let me consider this is a complex plane G and U be the open set inside the complex plane. And let us consider an element alpha belongs to this function of U. Alpha will be one of the element which belongs to function of U, that is mapping of an element alpha inside this set U. And moreover A will be one of the element of a open set U. Now we have to prove that f of A will be equal to alpha. To prove that f of A is equal to alpha, as A is an element of open set U, so every element in open sets maps into an open set. So this is the meaning. We have to prove that f of A is equal to alpha. Fine. Now by the fundamental theorem of algebra, we have already proved this theorem in first unit. Then if for any element in an open set, there exists a n number of zeros. So let me take an epsilon and delta such that for any open disk B of alpha comma delta will be contained in f of B of A comma epsilon. Right? Meaning is that whenever you are going to consider any ball inside this open set alpha comma delta, anyhow you have learned this concept in topology, so it is just a glimpses of it. So that will be a subset of function of B of A comma epsilon. Anyhow epsilon and delta are very small quantities. Fine. Now where we have to write B of A comma epsilon will be subset of U. Why? Because A is an element of U. See here, suppose if I have U here, A will be an element of U. Epsilon is small arbitrary number around A. So whenever you are going to consider disk around that point, so that will be A comma epsilon. Obviously that disk will be subset of the set open set U. Now let me take f on both sides. So you will get f of B of A comma epsilon will be subset of f of open set U. Meaning is, I have already known fact that f of B of A comma epsilon is contained in our B of alpha comma delta is subset of this set. So I can replace this as B of alpha comma delta. One and the same, right? So I can write this as B of alpha comma delta is subset of f of U. Fine. Now for each alpha belongs to f of U, meaning is for each alpha is an element in a set U. For each alpha belongs to f of U, there exists an open disk B. Meaning of this statement is, for each and every element in a open set U, there exists a open disk such that B of alpha comma delta is subset of f of U. Meaning is, f of U is a open set. F of U is if you know the concept of real analysis as well as the topology, you can understand this concept. Anyhow it is abstract. Let me convey once again. See here, what I have done is I have considered an open set U and an element in an open set. So A is an element in open set, epsilon is a point, arbitrary point around that point. Fine. So let us consider a open disk B of alpha comma delta. Clearly that will be subset of function of B of A comma delta. Why? Because A is an element of U. as well as alpha is an element of function of u. This is alpha belongs to domain of a function. Fine. So I can write f of b of a comma epsilon will be, what I have done is I have considered f on both sides of this function. So I can replace this with b of alpha comma delta, which is subset of u. Meaning is f of u is open set. So that is what we require to prove is every open set maps, every constant analytical function maps an open set into open set. Since I have taken alpha is an element in f of u, what I have proved is f of u is open set. So hence the theorem. And we have one corollary, just a statement you have. Every non-constant analytical function maps a region into region. Here you have a function, open set, in place of open set, region. It is applicable for region as well. That's all. Only the theorem proof is only 3 to 4 statements. So you just memorize these two statements. It is good to memorize both the statements. It is good to write both the statements in exam. Hope so it is clear. Now let me prove one more theorem. So here is the next theorem. It is called as Rouch's theorem. Statement you have to memorize. As usual, it is important. So let f and g are analytical in a simply connected domain D, and gamma is a simple closed positively obtained curve in D, such that I of gamma is subset of D. Assume that f of z is greater than g of z for all z belongs to gamma. Then f and f plus g have same number of zeros. So we need to prove that f and f plus g have same number of 0. That is 0 of f will be equal to 0 of f plus g. So this is what we have to prove is. So before proving this statement, I'll just give you a glance. Remember, 0 of any function is none other than integral with reference to integration and is none other than f dash by f into dz. Clear? You just remember this statement. And Cauchy's integral theorem in the first lesson I have done. That is integral over a closed curve f of z into dz is equal to f dash of z divided by f of z. It is one of the application of a Cauchy's theorem, right? F dash of z divided by f of z, or else I can write integral over f of z into dz is equal to 0. Standard theorem only I have written. You just remember this. Clear? So before proving the theorem only I am telling you, anyhow I will send you the notes, but in the notes steps are not clearly mentioned. So please while writing the steps, follow the video and try to take the running notes of only mathematical steps. Rest of the wordings and all you write by using the notes only. Wordings and all statement forms will be in the notes, and just a mathematical statement it was not clearly mentioned in the notes, so it is better to write by referring the video. Fine. Now coming to the proof of this statement, see what is the given condition in the theorem. It is f of z is greater than g of z, right? And f and f plus g we have to prove they have same number of zeros. Fine. Remember, if f and f plus g are analytical in D, as it is having condition is given in a problem itself, theorem statement itself. See here f and g are analytical. It is given in the theorem itself. So it is sufficient to show that integral over gamma f dash of z plus g dash of z divided by f of g plus g of z into dz will be equal to f dash of z divided by f of z into dz, right? So at the beginning of the session, at the beginning of this theorem I have told you zeros of a function is none other than f dash of by f into dz, right? So this is none other than 0 of function f, and this is none other than 0 of a function f plus g. So if we prove this statement is correct, the theorem will be proved. That is, both f and f plus g will be having same number of zeros. So hope you understand this step. Why I have written as definition of 0 of a function is f dash of x or f dash of z divided by f of z into dz. We have to prove zeros of f is none other than 0 of f plus g. So that is why I have taken this statement. So we have to prove this one. Now let me prove this. So I'll just take this to LHS side. So I can write the above step as f dash of z plus g dash of z divided by f of z plus g of z minus, I'll just take this into LHS. So I can write f dash of z divided by f of z into dz. Now I keep on simplifying this step. So I can write this as, you just write this LHS. In the notes also I have written the same. Please copy this step. Why? Because here there is no space to write, so you just write the same. So I'll take the LCM. So what is the LCM here? F of z into f of z plus g of z. So when you take the LCM, you will get f dash of z plus g dash of z into f of z minus f dash of z into f of z plus g of z. just LCM I have taken into dz. Now let me simplify this. Integral over gamma, I'll just multiply this, so you will get f of z into f dash of z plus g dash of z into f of z minus f dash of z into f of z, plus into minus is minus f dash of z into g of z divided by numerator denominator f of z into f of z plus g of z into dz. Now what are the terms that get cancelled? You just go through this. F dash of z into f of z and f dash of z into f of z get cancelled. Please copy the steps from the notes. I'm sorry, from this video. Why? Because steps are not clearly mentioned in the notes. So g dash of z into f of z minus f dash of z into g of z divided by f of z into f of z plus g of z into dz. Fine. So now I can simplify this as, I'll just do here, see here, I can write this term as, I'll just write here d by dz of g by f. If you differentiate this, you will get denominator square, denominator into derivative of numerator minus numerator into derivative of denominator. So if you cross multiply, you will get f square into d by dz of g by z as f into g dash minus g into f dash divided by, I'm sorry, nothing is there. Why? Because you have multiplied. So you can note that g dash f minus g into f dash can be written as this statement, right? So I'll just replace numerator by f square of z into d by dz of g of z divided by f of z. Hope so it is clear, right? So d by dz of g by f can be written as this. So if you multiply f square here, you will get f into g dash minus g into f dash. See here, g dash into f minus f dash into g can be written as f square into d by dz of g by f. That is what I have written. So denominator, I am going to take f as common. Anyhow, f is already there. So let me take one more f as common. So you will get f into f is f square of z. So 1 plus g of z divided by f of z. Why? Because we don't have f of z here, so we have to divide it. So this term get cancelled. So what you're going to get is, I'll just continue here. So what you're going to get is integral over gamma. So I'll just write here integral over gamma. See here what you have in the numerator, d by dz of g of z divided by f of z divided by 1 plus g of z by f of z. Right? Now what I'm going to do is, I'll just replace g of z divided by f of z with h of z. Fine. Just replace. So you will get integral over gamma d by dz of h of z divided by 1 plus h of z. So d by dz of h of z is none other than h dash of z. Right? H dash of z integral over gamma 1 plus h of z into dz. Now from the Cauchy's integral theorem, the value of this function will be 0. Integral over gamma is a closed curve, f of z into dz will be equal to 0. So therefore, by Cauchy's integral theorem, we can write what is the LHS. I am going to carry this LHS as it is. See here, f dash of z, I'll just write one more step. See here, f dash of z plus g dash of z divided by f of z plus g of z minus f dash of z by f of z into dz will be equal to 0. Why? Because this value is 0. Right? So LHS as it is, RHS value will become 0. Now I can write this statement as, see here, integral over gamma, I'll just write this as f plus g whole dash. When you're going to split, you'll get the same, right? So I can write this as f plus g dash minus integral over gamma, I can write this as f dash by f into dz. One and the same. I have just splitted this, and instead of z I have taken only f. It is understood f is a function of z. So instead of separate differentiation, I have taken whole derivative. If you differentiate this, you will get back the previous step. So let me shift this. Anyhow you have 0. I'll just put here only equals. So this is none other than 0 of a function f plus g. Right? See here at the beginning only I have written 0 of a function is none other than integral over gamma f dash by f. So here f dash, in place of f what we have, f plus g. So it is none other than 0 of f plus g is equal to 0 of f. That is zeros of f plus g is equal to zeros of f. That is what we need to prove is f and f plus g have same number of zeros. That is 0 of f plus g is equal to zeros of f. So hope so it is clear. See, all these steps are not explained in the notes. Please, whatever the statement is given, you just write down the same as in the given notes, and rest of the simplification, whatever the simplification is there, please go through the video and copy the same. Hope so these three theorems are clear, and moreover all these three theorems whatever I have done in this session is very important. So let me continue few more important theorems in the next session. Thank you.